Now we are continue from the previous series of videos where we done the calculation of area of reinforcement and the spacing of reinforcement in the two-way slabs, and we also calculated the depth of the slab. Now we like to check whether that depth, which is 150 millimeter, is satisfy the deflection requirement of AS3600. Now I encourage students to watch the video for the deflection of beam, where I have a detailed discussion about each parameters that we use. Here I'm not going in the great details, rather I will just go through the main difference that is followed for the slabs. So if you want to calculate average effective second moment of area, like you want to calculate I effective for 1 meter wide strip in determining using the short term serviceability load, please note that WS that we calculated for the strength cannot be used here in the serviceability. We need to use for serviceability, we can't use this factor load. Okay, if I can show it to you here in the previous video where we do not use this 9.6 kilopascal, which is the considering 1.2 and 1.5. We do not. This is for the strength only. Serviceability, we are finding the service load. Now to find the service load, we have a dead load plus short term load factors plus the times the live load. Now we calculated this dead load 4.3, and this was given in the questions, and the live load is given in the questions. I can show it to you. 4.3 in our calculations based on this thickness of the slab, we have calculated the weight 4.3, and I think the live load is given in our examples. Live load is given 3 kilopascals. So based on that, these short-term factors also given in our examples. Yes, let me show you that is given in our example 0.7. So it give me 6.4 kilonewton per meters. Now this 6.4 kilometers does not come onto this strip. How I draw this strip? I think if I take you back to this one here in these figures, if I'm looking for this strip, I draw this let's say 1 meter wide strip here for the slab. So this is the slab, 1 meter wide strip, and these are the supports. You can consider these are the supports of the beam, and these are 5.5 meter apart. Now if you do the structural analysis on these examples, you would see this kind of bending moment, negative bending moment at the support, positive negative bending moments. Now we are interested in this zone only. As you can see, we are working on this corner slab, so we are mostly working on this. Generally I'm not going in the detail of structure analysis, but I think for 1 meter wide strip we will have this at the left support WL square over 32, WL square over 16.8, and WL square over 10. We need to know what proportion of the load is carried in by this X strip. You can see here the total load is 6.4 kilonewton per meter. That is total W load coming, but this Y direction will carry proportion of the load, and on this strip will also carry some load. So we need to calculate what is the amount that strip will going to carry. So that can be, this is I take from there is no equation in the standard. I take this one from book. So Ly to the power 4 alpha Lx square plus Ly to the power 4. For alpha value it is given 1. 7150. I think this is a longer one. We done it in the previous video. We saw how we calculate this Ly. 7150 to the power 4 times 1 times 5150 to the power 4 plus 7150 to the power 4 give me 70.79. So in that case, amount of load carried by this X strip, the small strip would be 0.79. Around 79% of this 6.4 is 5.1 kilonewton per meter. So I would say that this Wx is 5.1 kilonewton per meter, and S stands for serviceability. Once you have that, if you want to calculate the design serviceability moment at the left hand discontinuous supports, let's say at here, left hand discontinuous support, let's say at here discontinuous supports, they have these equations, WL square over 32. We calculate 5.1 here times the length 1.5 meters. So please make a correction here. That is 5.15 meters. This is 5.15 meters. In the previous video we discussed this, how we get this 5.15 meters over 32. Give me the moment here 4.2 kilonewton meters. At the midspan here, it will be WL square over 16.8. So substitute again 5.1 times the length is 5.15 square over 16.5. It's give me the moment here 8.1 kilonewton. It's just the bending moment diagram, structure analysis. At the right hand, continuous support. So at this supports here, in this slab, that is continuous one, which has a divide by 10. So just numbers are changing. It give me 13.5 kilonewton meter here. Now moment of inertia, we have 1 meter wide strip, depth of the slab is 150, bh cubed over 12, substitute 1000 millimeter b, depth is 150 cube over 12, give me this moment of inertia, that is the uncracked sections. Okay, that's moment of inertia of uncracked sections. Now we need to find the cracking moment. For that cracking moment, there is an equations in the standards to find the cracking moment. Please note this is the pre-stress force, so we are not considering the pre-stress force. So P is 0, P is 0. Please check my previous video where we discuss in the details about this P. So over here we need to calculate this maximum shrinkage tensile stress. That can be calculated by using these equations here, where this one is a tensile reinforcement, this another one is a compression reinforcement ratio. We don't have any compression reinforcement, so we taking this PCW equal to 0, but PW we have tensile reinforcement. For the at the mid span we have 390. I can show it to you here. At the previous videos we found that at the mid spans we have reinforcement, tensile reinforcement 390 millimeter square per meter. So if I substitute that 390 AST, B is 1000 millimeters over the depth 119. So depth is 119. I think in the previous video we discussed that depth is 119 millimeters. That depth we discussed in the previous video. Equal to give me these numbers, and PCW equal to 0. Now once I know these values, I can substitute those values in these equations. 2.5 PW is 0.0033 minus 0.8, no compression reinforcement, so that is 0, over 1 plus 50 times 0.0033, Young modulus of the reinforcement 200 thousandths, times the strain is given in our examples, shrinkage, creep and shrinkage strain given in the example 700 times 10 to the power 6. Simplifications give me 1 megapascals. Now there is a one more parameters here that we're going to take into account, which is the Z, called section modulus. For uncracked sections, so for uncracked sections we can use this gross moment of inertia over YT. Now please note this YT is the distance. If I redraw this 1 meter wide strip, you have 150 millimeters. So from the centroid to the tensile reinforcement, that YT is 500. That YT is h by 2. So let's say your h is 150 millimeters, so that's h by 2 is given here. So this h by 2 is here, okay, from the centroid to here. So that will have bh cubed over 12 times 2 over h, so you have bh square over 6. So that bh square over 6 will give me 1000 times 150 over 6. So that 1000 is b, h is 150 over 6. That will give me this 375. I think the unit is millimeter cube. You can do same thing here as well. We calculated this I think in the last video we calculated this I. So you can also work it out. Z equal to I on YT, which is 281 times 10 to the power 6 over YT is 75. It will give me the same answers that are shown here. Once you know this section moment of section modulus, you can just go MCR, cracking moment, equal to Z times FCT F minus sigma S. I did not write this P over AG. P is 0 because no pre-stress force, and we don't have pre-stress force, so P over E is 0. So I substitute this 375,000. I think there are 4 zeros. Let me check whether it's a 4 zeros. So we can quickly check here. 1000 times 150 square over 6 gives me 4 zeros. So there are 375. So that is correct. 375 000 times 3.4, take away 1, and I think this one we calculated here. 3.4 FCT dot F. I think we calculated that characteristic strength in the previous video that I substitute here. That's give me the cracking moment 9 kilonewton meters. We will continue solving these examples in the following videos. Thank you.